This conference will now be recorded.
Hello, can you hear me? Andrew.
You can look in the chat room.
Okay, I could. So everyone can hear me, right? Okay. Let me see where the chat room. Okay. Okay, great. Okay, I will start. And I think we have 6 people online. And today I want to show you what my research has been over the past 5-6 years. And today I'm going to try to introduce you how we do early detection of cancer through DNA methylation analysis. I don't know how many of you have heard of DNA methylation. Can you write in the chat room? Have you heard of DNA methylation? Epigenetics? So if you can see my chat or hear me, you can type your answer. Okay, very good, Serene. Yes. So epigenetics, you know. How about everyone else? Okay, I have Sybil. Yes, wonderful. And I guess you guys are very advanced, even as a high schooler. And those are actually very, very advanced topic. And used to be taught mainly in graduate school. Now I think in undergraduate, we talk more and more about epigenetics, gene regulation by methylation. So today, my talk is, I actually gave the same talk in October 29, 2019 in San Francisco in 2019 World Alliance Forum, organized by George Harris, UN ambassador from Japan, and also the Ministry of Japanese Health Department. And so I will walk you through my talk there. However, before I do that, I want to show you the history several years ago, where we are now. Now you can compare where we are now. Okay. So can you see my screen? Okay, wonderful, thank you. So this is a talk I gave October 28, 2016 in Boston in the Next Generation Sequencing Congress. So at that time, I'm talking about more like a vision. How do we use non-invasive, how do we do non-invasive prenatal testing and cancer diagnostics by cell-free DNA and the NGS next generation sequencing? I don't know how many of you have heard of Down syndrome. Okay, so some of you have heard of Down syndrome. Basically, it's a neurodegenerative disorder. The baby are born with a trisomy 21. Basically, you know, each of us have 2 pairs of chromosome 1, 2 pairs of chromosome 2, 2 pairs chromosome 3, and then 22 pair, and then XY, right? We have 23 pair of chromosome. That's why there's a company in Bay Area called 23andMe. They're trying to do genetic testing and ancestry. However, in Down syndrome baby, they are born with 3 copies of 21. So it's called trisomy 21. The problem is that the child will display neurological disorder, development delay, and basically they have a problem with their IQ. And there's one way to actually test while in pregnancy before is through ultrasound screening. Basically, the doctors will to see how the baby develops. But usually the sensitivity is very low, maybe at a 40% of chance you can detect the baby having this problem. So there's still quite a few baby born with Down syndrome. And if a mother is older than 35 years old, then usually amniocentesis is recommended. Basically, the doctors will use a long needle to puncture through the mom's womb and get some droplet of fluid from the amniocentesis fluid. Then they do a cytogenetics to test if there's trisomy 21. It's an invasive process. And my research has been in collaboration with Professor Dennis Low in Hong Kong. Can we use blood, draw blood from mother, and then test if a baby has Down syndrome or not? So that's my research in 2007, published in 2010. Then we want to commercialize that technology, and further we want to commercialize the technology to cancer using same idea, basically through blood. So basically, we usually show a sign like conflict of interest, and because of me and my co-founder, Professor Kun Zhang, are both professors. I was an associate professor in biomedical engineering, and Dr. Kun Zhang is a professor now chair at the bioengineering at the UCSD. So we joined force to work on this problem. And you may have heard of liquid biopsy through CTC, ctDNA, cfDNA, or sDNA, or uDNA. All that means is CTC is a circulation tumor cell, or circulation tumor DNA, or cell-free DNA, or stool DNA using your stool, or urine DNA. So some of you may have already know right now the most popular thinking in the mainstream is how can we use blood to detect cancer early, right? And why that's possible, or how can we detect if a baby has a genetic disease through drawing blood from mom? And it has been found in if there is a cancer in the body somewhere, cancer cell will go into the bloodstream too. That's how they do metastasis. And also cancer cell die, and they will release their DNA into the bloodstream in fragments of about 150 base pair long. So it's more like a one round of DNA around the nucleosome. So you can imagine in everyone's blood, there are many DNA fragments flowing. The DNA fragment is about 150 base pair. They're called cell-free DNA. If they're coming from tumor, they call ctDNA, circulation tumor DNA. If they come from baby, we call cell-free fetal DNA. And you can imagine in the stool, also from your stomach, from your digestive tract, cell die, they also can release DNA into your stool, and same as urine. So you can imagine if you can develop a technology which can utilize those DNA analysis, maybe you can identify cancer without clinical symptom. One of the example I pioneered company called Exact Science. They are a public company, about $10 billion. They are spun out of a Mayo Clinic. They use stool to do colorectal cancer discovery. Basically, they send you a kit. You had to collect a bunch of stool, then send them back. Then they will analyze in the stool if there are certain genetic marker or epigenetic marker. And the genetic marker they use is a KRAS mutation. Epigenetic they use is more like a CEP9 and other DNA methylation marker. And this liquid biopsy using self-DNA has been used for basically drug selection, for targeted therapy, and for also managing resistance, if there is any resistance. And there is a Science Translational Medicine paper in 2014 have shown they can identify mutations and in basically cell-free DNA, and then you can use whatever drug, or if there is drug resistance. And for example, IRESSA is a drug approved by AstraZeneca to treat lung cancer. It's a tyrosine kinase inhibitor especially for EGFR. And one of my friends who cannot join today, his name is Bing, but he will be a judge. His brother actually was recently diagnosed with lung cancer, and under my recommendation, he did a broad-based test for identify a drug, and luckily he was identified, with the EGFR exon 19 deletion. And there is one drug called IRESSA, which is from AstraZeneca to treat. And the good thing about this drug is it has a very good survival curve for EGFR exon 19 deletion. So most likely the doctor already prescribed him with this drug, and hopefully he will be able to at least prolong a quality life for a number of years. And it's also expected, the drug is called IRESSA and Definitive, and it's also expected he will develop drug resistance down the road, more like 2 or 3 years later. But AstraZeneca also has a number of drugs that are targeting other mutation after a few years. And the same, I already make an introduction, in pregnant mother, the baby is growing in the womb. Before 1997, we thought in mother's blood, there is no baby DNA because there is a placenta acting as a screen. However, things changed in 1997. Professor Dennis Low from Chinese University of Hong Kong, using a very simple technique called PCR. So how many of you know PCR? So it's a very simple technique, right? A lot of high school kids nowadays learn. For example, Andrew, I know they are in very good, William, very good, Brianna. And so I know Andrew in CCA, Canyon Quest Academy. And in the quest, he took with Mr. Haas. They already do a lot of PCR cloning. So PCR is the most basic and important technique in molecular biology. They actually won a Nobel Prize for the innovator. So what Professor Dennis Low did is he was a physician from Oxford. He returned from England to Hong Kong. One of his research is, well, can we identify any DNA from baby in mother's blood? Most people tell him, no, you can't, because it's placenta. He don't believe it. He said, let me give it a try, because the experiment is simple. Can you guys think about a way, how can you test in pregnant mother's blood, they are baby's DNA? Can you think of a So let's pause for a second. Look at my chat. Can you think of a way to tell if there is a baby's DNA in pregnant mother's blood? Can you do experiment design? Can you think whether it is possible?
Yeah.
How?
Because, wait, what did you say again?
Can you see if there's baby's DNA in mother's blood
Yeah.
when you are in the mommy's womb?
You have to make sure there's 2 different types of blood.
Oh.
Because if there's 2 different types of blood, then you know, because this one might be the mommy's blood, this one might be the baby's blood. So then, and they might be, and the one that has the bloods, this that has the least air in the blood cells might, because it's a baby and he doesn't really know how to breathe yet.
Yes, good idea. Okay. So I haven't seen you answer, but my 7-year-old son, Alex, told me he can, if you can identify 2 different blood, one is a baby's blood, one is mommy's blood, then you know there's a baby in mommy's womb. Well, which is a very good answer. And
there might be different blood cells because
yes,
because there's 2 different types of blood cells, because one of them might not be a lot of red because the baby doesn't really know how to breathe yet.
yes, actually that's excellent. He said the baby don't know how to breathe yet.
No, not really.
Not really. And there are 2 types of cell, blood cell, and which is actually very correct in some way. And you can imagine baby got the oxygen from mother's blood. Right?
Because the blood cells, like they connect a little bit, so, and then baby takes a little bit of air from it, and then the blood cells go backward, and then some of it goes to the baby and some of it goes to the mommy.
Yes, that's right. Okay, that's a good answer. So basically, what happens is the baby's blood cells dies, and the baby's cell dies, right? And then it releases DNA into the bloodstream, and then it will cross the blood-brain barrier into the mother's blood. It basically cross it and go to the mother's blood. But how do you tell if there is a fetal DNA? You can use simple PCR. Remember I told you there are 23 pairs of chromosomes in everybody, and if mother is a female, so it has a XX, right? You guys know mommy has XX, and if it's a boy, it's XY, right? So male has XY. So you can see there's something different. What you want to do is you will take mommy with a male baby and a mommy with a female baby, and then non-pregnant mommy, non-pregnant female as control. So what you do is you design a pair of primer, basically which will target the Y gene, Y chromosome gene, right? So design a pair or more pair which target Y chromosome gene. Now you take the blood, spin down the plasma, get out of the mother's blood cell, then extract DNA, and those are cell-free DNA. Usually you can get 10 nanogram of DNA from pregnant mother's 1 ml blood. And 10 nanogram DNA is a lot because there's many copies of genome inside it. And there are more like 3,000 genome copies. Usually baby's DNA is about 5 to 20% in that 1 ml blood. You can imagine out of the 3,000 to 6,000 genome copy, there are about 600, between 200 to 600 coming from baby. So you can easily detect that because PCR has a very high sensitivity to detect a low copy number. So once you design a pair of primer, on Y chromosome, you have your control, which is a non-pregnant mother. Another control is a pregnant mother with a female baby. Your positive will be pregnant mother with a boy. So what you should see, can you guys imagine what you see when your PCR is done, when you run a gel or when you see a fluorescence, depends on. So in non-pregnant mother, she shouldn't have any fetal DNA. You should have a negative control, NTC. Then with a pregnant mother, with a female baby, it also acts as a negative control because the baby doesn't have Y chromosome, right? You should say negative. Now, when a female with a male fetus, you will see a positive gel run, right? So you know, if you saw a positive line of the Y chromosome gene product, while the other two are negative, then you know your experiment works. You detect successfully there are actually fetal DNA in pregnant mother's blood. So do you get the experimental design and the idea? Very simple, right? And this could win Professor Dennis Lo Nobel Prize in the future, and this is one of his pioneer work. But in order to detect whether it's a Down syndrome or not, which is more complex, a simple PCR won't do it. That's why Professor Dennis Lo found me in 2007 to collaborate, and we published a paper on Proceedings of National Academy of Science in 2008. Another paper, similar result, was published by Professor Stephen Quick from Stanford University. We all show we can use next-generation sequencing to detect Down syndrome because there are fetal DNA in pregnant mother's blood. And the commercialization was also done by US, by China, and I wrote another article to show this becomes a very promising non-invasive prenatal testing in a clinical setting. Then you can, this one shows you we can use a very simple statistic called a Z statistic to show if there are trisomy 21, you see an overrepresentation of chromosome 21, where you can show a Z score of a bar 3. And of course, using the same technology, you can also tell if the baby is a male or female. And in US, the first computation has been to tell if the baby is a male or female. But in China, this is banned because they are afraid of people selecting sex. So when a new technology comes, we have to think about the social and ethical consideration, not blindly just applying a technology to a commercial setting. So we have done a lot of technology development over my career and my co-founder career. Basically, they are supported by NIH, NIMH, and also private foundation. And two companies licensed our technology, Good Start Genetics in Boston and Pathogenics. Good Start was bought by Covens a number of years ago. And we also started a company called Singular Genomics. The idea we want to use our new technology developed for non-invasive prenatal test or oncology for early tumor detection. So I will skip. So the technology we are trying to use is called a Padlock probe or DNA tracers. So it's like a circle with two arms, and the arm is targeting your targeted area on your genome. So it's a targeted genome sequencing. It can detect SNPs, or most importantly, it can detect basically DNA methylation differences. So what we want to do is to use DNA methylation for early cancer detection using a technology similar to Padlock probe. We call it BSPP. And why we use methylation? A lot of paper basically published previously. I just show a few. For example, the Stradler et al. Nature 2011, Hansen et al. In Nature Genetics 2011, by my colleague at Hopkins, Professor Andy Feinberg School. They show actually in cancer and normal people, there is a very big difference in DNA methylation pattern. And they found there is an increased variation in cancer in the methylation, which is understandable because cancer cell, the gene expression is not well regulated. But in normal, every gene expression is tightly regulated. So if you look at the panel here, the Hansen et al., the blue are the methylation signal. You can see different blue line from normal people, they are very tight. But if it's a cancer, you can see the red line, the cancer methylation are high variation. And then it has also been known they are basically methylation area are usually in the promoter and corresponding to transcription factor binding, enhancer, and the chromatin structure. You know, the histone modification, which Professor Bing Ren at the UCD has pioneering. So we know in cancer cell, there are DNA gene expression misregulation, there are DNA methylation and chromatin, basically histone methylation variation. And we want to use DNA methylation as biomarker because we have very good technology to detect methylation in targeted area. And here is an example of Padlock probe, and we call it BSPP for DNA methylation analysis. It's called bisulfite Padlock probes. Basically, what you do is you treat the DNA, cell-free DNA with bisulfite. If the CG dinucleotide C cytosine is methylated, it will not change anything. But if the cytosine is unmethylated, the bisulfite treatment will change it from C to T. Once you sequence, it will read as a T. So you know there is a methylation. The DNA is not methylated in this CpG site. And we applied a pattern called Monod from UCSD, where in the blood, you can imagine there are regular normal blood cells. There are placental tumor cells. In the plasma is a mixture of, and also the tumor proportion is only about a few percentage. In the early stage, maybe only 0.1%. And the key is to identify methylation haplotyping, which means a number of CpG sites nearby, they are all either methylated like in black circle or unmethylated in white circle. You can actually use one string to count how many CpG on that one string as your biomarker. Now, if you can identify some biomarker which they are methylated in this haplotype in tumor, and but they are unmethylated in the blood cell background or in the normal cell tissue, then if you detect this black string, you know there's a potentially cancer. So that's a very simple premise. And we have done this at UCSD to show, can we use this to detect a tumor node where we can. For example, here you can see if it's pancreatic cancer, you have very high abundance of methylation in certain area. And then in the blood, you can see you have a corresponding some high methylation level. In normal plasma, you have certain background. So you had to subtract the background. That's why we build the background model. So we show very promising result in there. And especially we show one promoter ESR1, which is unmethylated in normal tissue, but it's a higher methylation in all different kinds of cancer. So it validates our technology can identify known, basically, cancer marker in methylation. And here just show you some variation. Then in different tumor, we show some pancreatic cancer, colon cancer, and non-cancer, we show some promising higher signal. So that's pretty much what we did in 2016. Now I want to show you fast forward in 2020. Okay. Can you see my screen? Okay, wonderful. Thank you, Brianna. So fast forward to 2019, October, I gave a talk, and our product is going through FDA trial now. We are going to have a meeting with FDA on April 21st. We are supposed to go to FDA in Maryland, but because of COVID-19, we can't. So we changed that to a basically conference call. And here shows you we can really go using methylation haplotyping analysis to do early cancer detection in different types of cancer. Why early detection is very important? Because personalized treatment has limited benefit. Even you guys know the new treatment, including the precision medicine and immunotherapy, has only extended median cancer survival by 2 months. So even with the drug, targeted drug, on average, patient only live 2.1 months longer, and the expense is usually $500,000. And for example, my friend's brother, 1 month he has to pay about $5,000. A year is more like $60,000 in China. In the US, it's more like $300,000. So most improvement in cancer survival is due to early diagnosis. Because when the tumor is still in the early stage, surgical removal is very effective. For example, like breast cancer, if there is a breast cancer screening, basically by simple surgical removal will be effective. Same thing with the colorectal cancer and many types of cancer. And this shows you early detection of cancer makes a difference. The survival rates is very, very different. If you detect it early in cervical, breast, colon, skin, ovarian cancer across cancer board, this is from NCI. Usually you can save 91 to 99% of people. For example, for cervical cancer, 9 out of 10 can survive if detected earlier. In breast cancer, pretty much everyone can survive. 99%. Skin cancer, 98%, which are very, very strong number. However, if you detect late, like stage 3 or later, cervical cancer, you can save about only 2 people out of 10. Breast cancer also about 2. Skin about 1.5. You can see the statistics are striking. Not talking about even about cost or quality of life. And I already told you, circulating tumor DNA is a promising marker, and we add in the methylation, ctDNA, circulating tumor methylation DNA is a very promising marker. The reason is we already know cDNA carries distinct epigenetic marker. Mechanistically, because DNA methylation affects gene expression, when tumor was a normal cell, at once tumor was good, right? It's like a criminal, and sometimes he's good. When it becomes bad, there are gene expression differences, and those usually are controlled by DNA methylation. And in 2 types of gene are very well known. One is the uncle gene, another one is tumor suppressed gene. Usually, uncle gene are suppressed, not expressed during normal development at a certain mature stage. But in cancer, they become wild, like tyrosine kinases. You saw, like EGFR. And then there are tumor suppressed gene, usually should be expressed. It acts as a brake. The tumor gene acts as a gas pedal, keep the car going. But then it needs brake. So in cancer, usually you have the gas pedal always on, but your brake doesn't work. And then that shows in DNA methylation. Basically in cancer, in uncle gene, there is a hypermethylation, so there are less methylation. But in tumor suppressed gene, there is a hypermethylation. So the tumor suppressed gene was hypermethylated, which are not expressed. So we want to leverage those biological knowledge. And especially we have a targeted methylation analysis tool called BSPP. So I already told you the CG dinucleotide, when they are together, if the cytosine is methylated, when you use bisulfite treatment, it won't be removed. If the C is not methylated, it will become uracil. When you do sequencing, it will become T. I already showed you we can detect tumor haplotype, with this one string of black. Then this tells you tell sign of a tumor. It's very difficult. As I told you, the fragment DNA is about 150 base pair, and the bisulfite treatment is very harsh. It damages 90% of DNA. If you start from 10 nanogram DNA per ml plasma, you only have about 3,000 genome copy. Less than 1% are from cancer. So usually about 10 copy from DNA. If you damage it to 90%, you only have 1 copy left. So PCR won't be able to do it. And it's very difficult. So what we have achieved how do we make this DNA conversion into library sequenceable, very high frequent, high efficient. Other people can do it at 20%, we do it at 80%, and then we use many markers to compensate for the loss. We have published a number of papers over the years from 2009 to 2019. You can see we published on Nature Biotech, Nature Method, Nature Biotechnology, and Nature Genetics. And recently we have another on the Nature series for review. So it's many, as you can see, 10 years to develop some technology, another 5 to 7 years to develop a product. It's a very long process for very innovative product. So I want to show you some results we did, and we are going to go through called Singular colon ES. It's a non-invasive early stage colorectal cancer detection. This is the one we are ready for FDA trial. And the colorectal cancer in the US, every year, about 145,000 new cases and 51,000 deaths. It's the second deadliest cancer. And as I told you, detected early, 9 out of 10 people can survive more than 5 years, which is considered a cure. And if it's detected late, 2 out of 10, it's about 1.5, survive 5 years. So big difference. Also, life quality, money, and family suffering is different. So in the US, CMS or insurance company actually pay for people over basically 50 years old to get colorectal screening using colonoscope. So we recommend everybody should get a colonoscope if you are 50 years older. Now the doctors even recommend, the American Physician of Doctors, Association of Doctors recommend now 45 years old to go to colonoscope. Do you guys know colonoscope? Have you heard of it? Okay, Malik, very good. So you have heard, right? Yeah, wonderful, Brianna. The problem with the colonoscope is you had to have a lot of prep. So basically, a day before, you had to drink a lot of basically things to get your stool loose, and then you have a run like a diarrhea, like, and then the next day you go, and then the doctor will basically take a anesthesia, then perform over a couple of hours to check your colon to identify any adenoma or any cancer or take any tissue. And it's pretty invasive. A lot of people don't like it, even though insurance pay for it. So it's not about payment. But about 35% of people refuse. So which result in 21 million people on screen in the US. And then if everyone can do colonoscope, we can reduce deaths by 30,000 a year. But 30,000 people waiting to die because they are afraid of doing something. And the quota's fear of colonoscopy is the reason. And 97% of patients refusing invasive colonoscopy will accept a non-invasive test. 83% prefer blood test. That's why we want to develop a blood test to remove people's fear or uncomfortable with invasive test. Like what we did with non-invasive prenatal for Down syndrome, taking blood instead of amniocentesis. And colorectal cancer in China, even about 376,000 new cases, 191,000 deaths. It's the fifth deadliest cancer. You can see it has more deaths in the US because China has 3 times more population. Also, in China, the diet, some people are not healthy, eating a lot of pickled meat, pickled vegetable. But in China, lung cancer is #1 because of air pollution, also smoking. Second has smoking. Stomach cancer second, liver third, esophageal fourth, colorectal fifth, and the pancreas is sixth. So we want to target colorectal because in China compliance is very low, even lower than here. In China, only about 1/3 of people comply. 67 people do not even comply. So in a study by Germany, even though there's a company in US I told you called Exact Science using stool, but the sensitivity and specificity are not good enough. They are good, but not that good. And also handling stool in your own home is not very easy. And the patient prefer blood to stool. That's an analysis. And also in that technology in stool, they cannot detect a very early cancer very good sensitivity. They only have about 45% sensitivity in adenoma detection. But adenoma detection is critical because if you can detect it even earlier, you can reduce cancer cell deaths by 2.6 times if you can improve detection from 7.4% to 52.5%. It's very, very important. Each 1% increase in the adenoma detection rate was associated with a 3% decrease in the risk of cancer, so which is very, very key. And what we have done with our initial study, we collected about 1,200 plasma from different patients in China, 137 plasma by San Diego. What we try to achieve is a superior performance to current blood-based CRC screening method at the similar price point. And we actually achieved that result in our initial Shanghai study after 2.5 years, about $60 million. We have shown we can detect a very, very high specificity, about 98.7% specificity. Then in advanced adenoma, 87%. In colorectal cancer, 93%. In our San Diego follow-up study, we have archived the plasma sample. We replicated the study. We achieved about 95% specificity and 90% sensitivity. We don't have much adenoma here. We are in the process of collecting. That's our clinical trial was about. So the conclusion is that we have achieved a very high accurate blood-based non-invasive assay for early colorectal cancer and advanced adenoma detection. Future work is that we want to study a prospective study to determine if this screening improves patient outcome and is cost effective. That's why in the summer or fall, we are expecting to start a FDA trial. It's a PMA 10,000 patient trial, prospective. Well, after this trial, if we have good result, we expect to get FDA approval and go to market. You can imagine, guys, it will take us 10 years to develop a technology, 5 years to develop top product, and another 2 years to go through FDA. So this is more like a 17 years process. It's a long, but as scientists, this is what we are proud of. And that's why we encourage you guys to take on the biology and bioinformatics from early on, accumulate your knowledge, have a goal. And we, after 5 years, 6 years, we only have one product. Of course, we want to do other cancer type. The problem is every cancer is different, will be different marker, will be difficult. So I welcome you to think about the ways to do esophageal, lung, liver, and you can start to see different companies are focused on different area. This is what I want to leave you with. Think about what you want to do, and then learn how to do experimental design, how to do molecular biology, how to do bioinformatics. That's all the Helyx was trying to ready everybody around. And I'm glad to talk to you about our research. I hope we can inspire you to basically pursue a career in life science, medicine, or bioinformatics, or any data science. And thank you. If you have any question, please feel free to use the chat room. I think we have about 7 minutes left. Thank you.
This conference will now be recorded.